The first speaker of this afternoon is Richard Siefring from Bochum, and we'll talk about symplectic field theory of codimension 2 stable Hamiltonian hypersurface.
So, thank you for the invitation to speak here today, and thanks for organizing the conference. So this is work that sort of aims to bring into higher dimensions some work I've previously done in 4 dimensions. I actually spoke about that work here, I think, 6 years ago. And so for those of you who've seen me speak about that, this follows a very, very similar script. It's just, there I wanted to talk about how to count intersections between 2 non-compact holomorphic curves. Now I want to jump up to higher dimensions and talk about how to count intersections between a non-compact holomorphic curve and a codimension 2 holomorphic hypersurface. And it turns out a lot of the same thinking that works in 4 dimensions works in higher dimensions. So just a quick sort of conceptual overview of what's going on, and then I'll get into some of the details in more detail. Details in more detail, great. So we're going to have an odd dimensional manifold that's equipped with a vector field. More details on that in a moment. And we'll look at the cylindrical manifold R cross M. So this is now even dimensional. And this will be equipped with an almost complex structure, an R-invariant almost complex structure. Almost complex structure J. So that is a section of the endomorphism bundle of the tangent space, which squares to negative the identity. Okay, and so we will study maps here from Riemann surfaces with punctures. So we take out a few points and we map these into here so that they are J holomorphic, or the derivative is J linear, complex linear. And these things will be asymptotic to periodic orbits of this vector field. Okay, so they should look something like this. And so in addition here, what I want to consider a codimension 2 submanifold in M. And I want this submanifold to be tangent to, or invariant under the flow. I want, let's say, the vector field X to be tangent to the submanifold V. And moreover, I want to assume, under the conditions we'll look at, this is no problem, I want to assume that R cross V is a holomorphic object. It's got a J invariant tangent space. Okay, so V maybe is in here like this. And now I want to understand the intersection behavior between curves and such submanifolds. So the sort of the big picture, the long-range goal would be perhaps to put additional structure on symplectic field theory or contact homology or any of these theories that count holomorphic curves by adding this intersection data with such submanifolds. And so we can say the intersections are isolated. Am I writing large enough? Bigger? It's okay. Isolated and have a positive local index. But there's a few potential technical problems with defining an intersection number or just counting intersections between these objects. So potential problems here. The first one is, so we would hope to be able, given this, we'd hope to be able to define an intersection number by summing local intersection indices. But the non-compactness here makes it not obvious that that's finite. It's conceivable that we could have a sequence of intersections running out the ends here when this curve, here is R cross V. They look like they've got the same dimension, but R cross V is codimension 2 in the whole space, and here's my curve here, that's dimension 2, so they add up correctly, they should have an intersection number. When this guy is asymptotic to an orbit that's in the flow invariant submanifold, it's not obvious that I couldn't have a sequence of intersections approaching infinity and then potentially an infinite intersection number. That turns out to be okay, and I'll explain, well, we'll see why later. One problem which is unavoidable is homotopy invariance. So even though the number is going to be finite, it turns out when this curve approaches this flow invariant submanifold and doesn't actually live in the submanifold, I should add that condition. I want to consider things that aren't contained in the submanifold but have ends that approach that submanifold. It's conceivable that you can lose intersections out infinity, or they could show up at infinity. And this actually does happen. This is unavoidable. But it turns out we can quantify what happens when we lose intersections that are infinity, and or they run in from infinity. And so we can define the intersection number, but the problem is it's not homotopy invariant. And so ultimately the question is, what can we say that's topological? Can we, for instance, get a bound on the number of intersections? And in ideal cases, say that a curve doesn't intersect this submanifold at all. And it turns out that we can. So basically, I'm going to, my outline here is I'll introduce some basic theory. And then I'm going to actually look at a concrete example. And this is where this will really start to look a lot like what I used to talk about when I did this in 4 dimensions. If you look at a nice enough example, you can turn this equation that's highly coupled and nonlinear into something where the components you're interested in all decouple, and the one component you're really interested in turns into a linear equation, and you can write down the solutions directly and really just study this and see hands-on what happens. And then the punchline will be, when I state the main theorems, that kind of once you do enough analysis, what happens in this concrete example essentially is the same thing that happens in general. So then I'll state my main theorems, which address that. So the basic background theory, we've got an odd-dimensional manifold that's going to be equipped with what I'll call a stable Hamiltonian structure, which is a pair omega lambda, where omega, I used to always write lambda first, and then I decided omega is kind of more important here. So I write it first now. Omega is a 2 form. On M, lambda is a 1 form. And there's going to be 3 properties here. So first property is that lambda wedge omega to the n is a volume form. Okay, and so what this ends up giving us is a splitting of the tangent space at each point. So it tells us that omega has at most a one-dimensional kernel. So kernel, and by that I mean the kernel of the map that takes a vector v to the contraction of v with omega. That's one-dimensional. Okay, and then the kernel of, did I say lambda? I meant omega. Kernel of omega. The kernel of lambda then will be a hyperplane transverse to this line bundle that's the kernel of omega. So we get this splitting of the tangent space into a line bundle that's kernel omega, and we can actually break that down further by looking at a vector field xh in kernel omega that normalizes to length 1 with this 1 form lambda. And then the other component of this splitting is this hyperplane distribution, kernel lambda, okay, which I'm denoting by C. And this condition also implies that omega restricts to a non-degenerate form on C. So I get actually a symplectic vector bundle. And the two other conditions here that are important in this definition of, I didn't say these are called stable Hamiltonian structures. I'm sure that's too small for anyone to see, but I'll write it anyway. Stable Hamiltonian structure. So I want omega to be closed, and d lambda should vanish on this, on the kernel of omega. It's equivalent to say it vanishes on that vector field. And so these two conditions together imply that the flow of x, which I will call the Rabe vector field, preserves this splitting. With the additional data of this symplectic structure on the hyperplane. So there's a few major classes of examples. I apologize to those of you who are experts and seen a lot of this before, but I think there's some younger people who maybe this might be new to. So first is contact manifolds. So for me, a contact manifold will always have a contact form. I know for contact topologists, generally the structure is the more important thing. So a contact form, lambda is a contact form if lambda wedge d lambda to the n, this is 2n plus 1, is a volume form. Okay, and so in this case, the pair d lambda comma lambda, or in other words, omega equals d lambda, gives me a stable Hamiltonian structure. So in this case, the hyperplane distribution C is just the kernel of lambda. That's what's known as the contact structure. And the Rabe vector field is what traditionally in contact topology has been known as the Rabe vector field. Second major class of examples is mapping tori. I guess they're not exactly mapping tori, but I'll call it that. Mapping tori of periodic Hamiltonians. So this is going to be important in the concrete example I do later of intersections disappearing. So here we're going to consider our manifold will be S1 cross a symplectic manifold. So this is symplectic. And this will be equipped with a Hamiltonian, or just a smooth function, smooth real-valued function. And so the stable Hamiltonian structure here will be defined by the one form lambda will be d theta, where theta is just the variable in S1. And the two form will be, I should check my signs here. Omega, I'm suppressing a pullback in my notation here, but hopefully you'll indulge me on that abusive notation. Minus dh wedge d theta. So the hyperplane distribution here, kernel lambda is just the tangent space to W everywhere, or the pullback of that distribution, I guess. The Rabe vector field, X, is d theta plus xh, where xh is the Hamiltonian vector field. Defined by the contraction with omega is minus dh, where this d here is referring to just the derivative in the w component and not the S1. And a final important class of examples is principal S1 bundles over over symplectic manifolds. So M, how do we usually denote this? So this is a symplectic manifold. I've got a principal S1 bundle. We can get a stable Hamiltonian structure here by having our 2 form B, just let's name the projection pi, be the pullback of the symplectic form, and our 1 form be a connection form on the bundle. So in this case, the hyperplane distribution, that is kernel lambda, is just the horizontal distribution of the connection. And the rate vector field, x, is just the infinitesimal generator of the S1 action. And this is kind of an interesting example for what I'll be doing, because in this case, there's a correspondence. We could put an almost complex structure here, and it turns out there's a correspondence between closed holomorphic curves here and punctured holomorphic curves upstairs. Meromorphic sections of the bundle give me punctured holomorphic curves in the, I haven't defined those yet, but in the stable Hamiltonian structure. And so when I define an intersection number for non-compact things, ideally when we project down to, at least in this case, when we project down and I get closed things, they should agree with the traditional homological intersection number as a sort of sanity check. And that will, in fact, be true. So let's talk about punctured holomorphic curves. And I should mention I use the word holomorphic and pseudo-holomorphic interchangeably. I'm a little sloppy about that sometimes, but it's sort of become standard in our field. So here we're going to have a M equipped with a stable Hamiltonian structure. And we can define what's called a compatible almost complex structure. Or let's say complex structure on C, which is this kernel of lambda. So everywhere we've got that splitting of the tangent space, and we want to define a complex structure there. We say it's compatible if, so we'll have an endomorphism of C. It should square to negative the identity. That's a complex structure on C, and it's compatible if this is symmetric and positive definite. And so given this data, we can then define what are called, what R invariant, not what are called, we can extend this to an R invariant almost complex structure on R cross M. I'll name that thing J tilde. So how can we do this? On R cross M, well, let's look at the tangent space there. We get a splitting as the tangent space to R. I'll name my variable in R A, plus the splitting we had on M. So that's R times the rate vector field plus C. And so what I'd like J to do, the action, should just be the J I chose there. And here, this is R plus R. We can essentially think of that as C. And so in the first component, we want it to be just behave like I. Okay, or more concretely, we can say J times dA is X, and then J on the hyperplane distribution is just the one we chose. Okay, so I don't want to get into the finer points of energy, but there is a notion of energy here. I didn't talk about holomorphic curves yet, so we'll consider now, given this J, a Riemann surface, so a closed Riemann surface. and a finite set, gamma. And look at maps U from sigma minus gamma to R cross M that are holomorphic. And so there is a notion of energy. To de Fleur or Hofer, depending on the context, which guarantees that curves with finite energy. I'm going to be sloppy about the word curve, too. You could call this a map or a curve. Sometimes people reserve the word curve for equivalence classes where you mod out by reparametrization. But there's a notion of energy that guarantees curves with finite energy are asymptotic to periodic orbits. Okay, so it's that picture I drew earlier, where I've got R cross M, and I've got this vector field here, and the images of the maps should look something like that, where near the ends they're converging towards cylinders over periodic orbits. I didn't point it out here, but this condition right here tells us that things of the form R cross flow lines have a J invariant tangent space. So it's these things, R cross periodic orbits, are already holomorphic objects. So it's kind of natural that these things should converge there. Not natural, but at least not unexpected. Okay, so now let me introduce the notion of a strong, stable Hamiltonian submanifold. So these are the things I want to intersect with my curve. So a submanifold, so I'm still dealing with M with a stable Hamiltonian structure. A submanifold is said to be a stable Hamiltonian submanifold if, let's put an inclusion map here, the pullback of the stable Hamiltonian structure is a stable Hamiltonian structure on V. And I'll say it's a strong stable Hamiltonian submanifold if, in addition, the ray vector field from the ambiance manifold is tangent to V. Or that should be equivalent to requiring that the ray vector field of this pulled back stable Hamiltonian structure, when I then push it forward by the inclusion map, agrees with the ray vector field of the ambient manifold. And I'll be mostly interested in the codimension 2 case, like I said, because I want to count intersections, and that's what I need for that to make sense. But some of the basic theory makes sense for higher codimension. So when I'll show that generically there should be no intersections if it's higher codimension, but they can exist, right? So you can still show that the intersection, there'll be a finite number of them and things like this. So it's good to, yeah, we can consider other codimensions. So let's look at a couple examples. I'll be completely honest. You know, people often say math, it's kind of, there's this parable about the drunk who lost his keys and he's looking under the light, not because that's where he lost them, but because that's where the light is. And so for me, I was thinking about, years ago, after I submitted my 4-dimensional paper, what can I do to push this into higher dimensions maybe? And this was the condition that made things work. And it seemed unnatural to me at the time, but as I spoke to a lot of people over the years about this, people would say, no, I know an example of this, and I know another example of this, and it turns out there's actually quite a few that I think arise quite naturally. So I'm taking a long time here, so maybe I won't give all of the examples, but I'll do a few. So there's this correspondence between, so not correspondence, but given a Riemannian manifold, just pretend that says Riemannian, and G, we can look at its unit cotangent bundle. And equip this with the tautological one form. And so this is a contact manifold. And over here we've got a geodesic flow. Which lifts to Rabe flow over here. And so within Riemannian geometry, there's a very natural notion of a totally geodesic submanifold. Okay, and so totally geodesic submanifolds are things where if we start with a point in the submanifold and a vector tangent to that submanifold, then the geodesic stays in the submanifold indefinitely. We do that for any point in any tangent vector. These then, under this correspondence, will lift exactly to a strong, stable Hamiltonian submanifold. A strong contact submanifold, actually, in this case. So in the case of a contact manifold, this notion corresponds to what's sometimes called a strong contact manifold. So it's a submanifold where the pullback to the contact form is a contact form, and the Rabe vector field is tangent to it. Another class of examples, since this is a dynamics conference, let's stick with a nice dynamical example. And so that is the three-body problem. So the restricted circular spatial or planar three-body problem. So there's a couple examples that arise here. So it has been shown by Albers, Frauenfelder, Van Coort, and Paternine. Sorry for not writing out all names. I don't remember the years, but just below and just above the first Lagrange point, which is a particular energy of this Hamiltonian system, the regularized energy surfaces, so you have to remove, I'll explain a bit more in a second, regularized energy surfaces are contact manifolds. Okay, so let me actually explain a bit. I'm going to have two massive bodies which are rotating in circular orbits about their center of mass, and I pick a coordinate system where they're fixed. And so the spatial problem is, in either case, I'm going to look at a massless body that's moving in this gravitational field. Planar problem, it's moving in the same plane as these two. Spatial, I can go outside. Okay, so there's a very natural, so regularization has to deal with collisions. You can sort of remove collisions with the massive bodies if you're clever enough. And so once you know these are contact structures here, there's a very natural example, which is that the planar problem within the spatial problem is exactly a flow invariant codimension to hypersurface. Okay? And then there's a second one that arises, which is as we pass this Lagrange point. So the first Lagrange point is sort of the first critical energy level. And so for very low energies, there's kind of three possibilities. We could be staying around one massive body, staying around another massive body, or not be near either of them. So if we're considering these sort of compact regions where we're staying around one massive body or another, as we cross that Lagrange point, now these manifolds look like we get a connected sum of two manifolds. Okay, and so right in the middle of this connected sum, there should be, what dimension I'm in? I'm in 5 dimensions, and this is going to look, the sort of neck of the connected sum is going to look like R cross S4. And so if I go right in the middle, there's going to be, kind of at the equator here, a flow invariance S3. Okay, so in this problem, there's a second. This is also a strong stable Hamiltonian submanifold or strong contact submanifold in this language. And so there might be interesting things that come from looking at trying to count holomorphic curves and counting intersections with that S3 in there. So one more example I want to mention, and sort of another motivation for this problem, is going back to this this principal S1 bundle picture. So here's M. I've got a principal S1 bundle over a symplectic manifold. And like I said, there's a correspondence here between closed curves here in the base and meromorphic sections of the bundle. You know, so we look at R cross M. And the R and S1 part is like C, so we can look at meromorphic sections of the bundle. And so there's a notion of the study of the sort of holomorphic curve theory that counts closed curves in a symplectic manifolds, Gromov-Witten theory. There's a notion of relative Gromov-Witten theory. So if we have a codimension 2 submanifold here, so V is codimension 2, there's a notion of relative Gromov-Witten which counts things, it sort of ignores curves in the submanifold, modulo the problem that you can't completely ignore things in the submanifold, because things that don't live in the submanifold could lose, in sort of compactness, could lose pieces into the submanifold. So you ignoring it up to a lot of technical detail that I don't want to talk about. And then given this, there's a symplectic sum formula. For Gromov-Witten. Okay, so these things are due to, well, so I should say first the symplectic sum formula is when I've got two different symplectic submanifolds. They're symplectomorphic, and the symplectic normal bundles, I think, should be anti-symplectically isomorphic. And then what you can do is cut out the submanifold and sort of do a connected sum in the fibers. So it's a way of constructing symplectic manifolds out of other symplectic manifolds. And you can get a formula for how the Gromov-Witten invariants of the surgered manifold relate to the unsurgered manifold. So this is due to, you know, Parker or Ruan Lee. And I should say there's some dispute about the correctness. Tirani and Singer have a very long paper where they discuss things they don't agree with here. That's all not interesting to me. What's interesting to me is that there is something here that should be correct. So something like this idea works. And so the point is, once I've got this codimension 2 submanifold here, if I look at the pre-image upstairs by this projection, this again is one of these flow invariant stable Hamiltonian submanifolds. So there should, corresponding to this relative Gromov-Witten symplectic sum formula be some sort of relative SFT and symplectic sum formula in SFT upstairs, which would contain this as a special case. Actually doing this is very, very far off in the future, but this is another motivation, another case where this sort of structure arises very naturally, and another motivation for considering such things. Okay, so now let's talk about the example. I think what I neglected to say here, that I meant to say, is that given one of these stable Hamiltonian, strong stable Hamiltonian submanifolds, we can always choose our J. It's a non-generic choice, but we can choose our J so that R cross V is J holomorphic. So how do we do that? Well, along V, if I look at Tm, where T R cross M along R cross V, I can sort of further break down the splitting I had here. I've got TR, I've got the component from the red vector field, which is tangent to V, and then I've got kernel lambda in M, but I can break this down into two components. C intersect TV, which will be the kernel of the pullback one form in V under my assumptions, plus, I'll name this C prime, the symplectic complement. Okay, and so I need to define my J here. So on the first component, it's already fixed. It just behaves like C. I can just choose one here. Because this is a symplectic splitting, I can choose a J here and then extend it there. And so when I've made that choice, this here, TV, will be, have a J invariant tangent space. Okay, so this is now the picture I want to understand. I've got M, I've got V inside, I'm looking at R across this. And now I want to understand curves that don't live in V but have ends that are asymptotic to periodic orbits in V. All right, so let's look at this example where I can write things down explicitly. Hopefully I have time. So my manifold here is going to be S1 crossed with R2, and we'll equip that with its standard symplectic structure, crossed with your favorite closed symplectic manifold. That component is going to be not interesting to me, because all the interesting stuff is going to happen here. So here's S1 cross a symplectic submanifold. I should say I'm going to consider this as R mod 2 pi z to save me from having to write a lot of 2 pi's later. And so let's put a Hamiltonian on this, an autonomous Hamiltonian, which will be 1/2, I'm going to put a subscript on it, alpha. 1/2 alpha R squared, where R is the, in polar coordinates, just the radial coordinate on R2, plus just your favorite autonomous Hamiltonian on W. I'll put a pullback there, but I might get sloppy about writing that. And so now the stable Hamiltonian structure here should be the one I wrote down earlier for mapping tori. I'm going to call my variable here now T. So lambda, the one form, is just going to be dt. Omega, the two form, will be, I'm going to, again, suppress my pullbacks. The pullback of the symplectic form on that manifold, plus, or I think I have minus dt dh alpha wedge dt. So the Rabe vector field, which I'll denote by x alpha, so this, the dynamics decouple here. I have here the Rabe vector field is, or actually let me write it like this. It should be dt plus alpha d theta, where theta is the polar coordinate here. Plus the Hamiltonian vector field in this component. Okay, so the dynamics here, transverse are just going to be rotating here, and just whatever they do there. That's not really so important. Okay, and now I want to well, first of all, note, let's find a nice stable Hamiltonian hypersurface here. So the stable Hamiltonian hypersurface, the codimension 2 guy, is going to be S1 cross with 0 cross with W. Okay? So that is fixed by the flow of this vector field. All right, and so I need to choose J. So let's write it in matrix form, with this being R cross S1, R2, W. R cross S1, R2, and W. So on the, or I should put T's in front of these, tangent space. On the W component, I'm just going to pick any almost complex structure that's compatible with the symplectic form. On R2, I'll pick I. So this here is the kernel of lambda. I'm free to pick my J there. And then this will be 0 and 0. And now I need to make sure the R component is getting mapped to the Rabe vector field. And the choice that does that is going to look like this. It's going to look like an I there. I'm going to get a 2 by 2 matrix here on R2 and something else here where delta xy is this, and gamma down there, that piece there is the Hamiltonian vector field of the part of the Hamiltonian on W, and then minus J times that. Okay, this part is not so important for what's going to come up. Okay, now given this, here's an exercise. I want to consider a map from a half cylinder into R cross M, or S1 cross R2 cross W. That looks like this. So the first component goes to S, the T in S1 goes to the T in S1 there, and then I'm going to have this H of ST in R2, and this is sort of the normal component to W, and then the tangential component to W. And you can check that the equation U satisfies the J holomorphic curve equation exactly when these maps H and K satisfy these equations. I mean, this is Floer theory, and since my Hamiltonian decouples, I get the Floer equation for both components here. So the Floer equation for K, that's less important to me, looks like this: Ks plus J kt minus the Hamiltonian vector field equals 0. It's easy to construct solutions here because I considered an autonomous Hamiltonian. Just gradient flow lines will work once I picked an appropriate metric. The H component looks like this. That's also the Floer equation, but I've written it a little different. Because the Hamiltonian's quadratic, it turns out the Floer equation becomes linear. And so this actually looks like ds minus AH, where A is this self-adjoint operator minus I ddt minus alpha. Okay, so we can write down solutions to that explicitly. So check that solutions to, let's call this equation star, and we can solve it with Fourier series, essentially. Solutions to star are of the form we get a coefficient e to the I kt, and then e to the k minus alpha s. So that is the general solution of that equation. And I said I want these things to converge to, so let's not lose sight of what's going on here. I've got this stable Hamiltonian hypersurface, and I want them to converge to a periodic orbit in V. So the h component should be going to 0. So in order to guarantee that happens, h going to 0 at infinity, I only want to consider k less than alpha so that this exponent will be negative. Okay, so given that, I can write down now a family of maps. U epsilon st. So st h epsilon k. So let's say we just picked a solution k, and now h epsilon will be, anything of this form works. So I'm going to put epsilon e to the minus 1 minus alpha s plus epsilon to the minus 2 minus alpha, I left something off here, e to the minus I t, and then plus e to the minus 2 minus alpha s e to the minus I 2t. Okay, so that's a sum of that form. And now I want to count intersections of u with v. It's just a parameter. Yeah, it's just a parameter. Alpha is in R. I could just pick a number, and for this example, I think it'd be nice to say it's between -1 and 0, but it doesn't really matter. I could have just picked. Any number works. I probably won't have enough time to get into details where I play around with the alpha and show kind of how it changes things. But so I want to count intersections of u and v. And if we look at the form this takes, v is where this component is 0. So counting intersections of u with v turns out to be equivalent to counting zeros of h here. So the intersection number is count of zeros of h epsilon. I forgot, I'm going to put that epsilon in there, because the point is the answer I get is going to depend on epsilon. So what's the count of zeros of h epsilon? That's a map from a cylinder to R2. This is just the normal component. It's like mapping to R2. So the count of zeros of h epsilon is equal to the winding of h epsilon s for s large minus the winding at 0. All right, so let's take a look here. I did this so I have to walk as far as possible to do this. So for s equals 0, let's just say we picked our epsilon small enough so that this term is much smaller than this term. So this is the dominant term. In that case, the winding here is going to be the winding of this term, which is -2, regardless of the value of epsilon, provided it's small enough. What about here? So S large. For S large, regardless of how small we chose epsilon, this term will eventually dominate this term, because this term dies off that much quicker, provided epsilon's not 0. So if epsilon's small, the winding for S very large is just -1, the winding of that term. If epsilon's 0, this term's not there. The winding for S large is that. So for epsilon not equal to 0, we get -1 here. For epsilon equal to 0, we get -2. So what's the intersection number? In one case, it's -1 minus -2. It's 1 if epsilon's not equal to 0, and it's 0 if epsilon's equal to 0. And so what's happened here is as epsilon goes from a non-zero number to something equal to 0, this intersection we had, one intersection has disappeared out the end. Okay? But that's something that's quantifiable. Right? Here we've got this normal description of our curve in terms of these Fourier series. And what we see is now, in a sense, the degree of tangency has jumped as it's increased as that epsilon's gone to 0. Right? As epsilon goes to 0, now the measure of tangency is now here. I mean, it's increased. The sort of the rate at which U is approaching the submanifold is increased. And if I choose my alpha here, nothing can come at infinity. So a intersection disappearing out at the end corresponds to an increase in tangency. An intersection appearing at the end corresponds to decreasing the degree of tangency. So I'd have to now add higher order terms that have less tangency, slower decay. But if my alpha is here, then I've got no more terms with k greater where I still get the negative exponent I want so that this thing's converging to the orbits. Okay, so the point is I can lose 1 out at infinity, or it can come back in as epsilon goes from a non-zero number or from 0 to a non-zero number. But when epsilon's non-zero, I can't get anything new at infinity. Okay, and so you can see that quite directly in this example. So in the about 8 minutes I have left, I really like this digital clock here. That's very nice. Let me sort of explain sort of what is true in general. So the punchline is this, once one has done the appropriate hard analysis, this example captures basically almost all the generality of what can happen here. So here's a theorem that will be in my paper. It's stated in the preprint I mentioned earlier, and hopefully this will be, let's say, 19-ish. I really, really hope to get this done within the next month or so. But the setup is this. Same picture I keep drawing, but let me draw it one more time. I've got this M with a stable Hamiltonian structure, V is a strong stable Hamiltonian submanifold, and I'm going to have a half-cylinder U in here that doesn't live in V but is converging to a periodic orbit in V. And so V will be codimension 2. So I look at the symplectic normal bundle here, which then, once U is close enough, lets me decompose it into sort of tangential and normal components. And the theorem on the asymptotics is U, the normal component of U, that's U is my half-cylinder. And I'll assume it's positive. I could also do a negative version. The normal component of U has a well-defined winding bounded above by, and I'll explain what this is. Let's say U is converging to an orbit gamma up here. This. So what is this? This is the normal Conley-Zender index. I've picked a trivialization, which I need to do if I want to talk about winding. But for large enough values of S, if I'm going up, S is my R component in the cylinder, for large enough values, the normal component's non-vanishing, therefore it's got a well-defined winding, and that winding is bounded above by what's called the normal Conley-Zender index. So along V, the flow splits into, the linearized flow splits into tangential and normal components. And so I can look at the normal linearized flow and compute a Conley-Zender index like normal. Like usual, let's say. I don't want to overuse the word normal. And that is the normal Conley-Zender index. So given that, one can, I should mention one can generalize a bit too, and this will be done in my paper. Instead of just considering cylindrical manifolds, I could also consider non-cylindrical codimension 2 holomorphic objects that are asymptotic to such things, just like I do with the curves. And it works there. And then also, of course, when we talk about holomorphic curve theories, especially outside of dimension 4, transversality is always a problem. We have to introduce abstract perturbation schemes and things like this. It turns out U doesn't really genuinely need to be holomorphic. The normal component just needs to satisfy a partial differential inequality that says the normal component is almost like it would be for a holomorphic curve. And you get the same result here. And so that I think would be pretty important if you ever want to do anything with this for a theory, because this transversality is so important. So given this, though, I make a definition, which is that if I've got now a punctured curve, there I was just considering a half cylinder, but let's consider one of these punctured curves. I want to define a product that looks like this. I take U, I pick a trivialization phi at every periodic orbit that's an asymptotic limit that lives in this submanifold, and I push U in a direction away from V in the direction determined by that trivialization. And then I add on, so let's say at a puncture Z, U is asymptotic to an orbit gamma Z. I want to sum over all such punctures where that lives in V. And I'd want to add on this term. Okay, so this is this weird product that one can define. It depends on a choice of trivialization over here, but the fact that I left it off over here seems to hint at the fact that it doesn't there, and in fact it does not. The trivialization dependence of these two terms balances out. And so the theorem then says, so U should be holomorphic. Let's say U is not contained in V. Then this product is equal to the actual count of intersections plus a term I'll call delta infinity UV, which is something that one can make precise. This is sort of a count of intersections at infinity, or count of tangency at infinity. Count of a normal tangency at infinity. And so that can be made precise in terms of how this normal winding differs from this maximum possible. It's essentially the difference at each puncture. I look at the normal winding. At each puncture that goes to the submanifold, I look at the normal winding. I take the difference between this and the normal winding. And so what I get is that's equal to that, and both of these terms are non-negative. And from the definition, this thing's obviously topological. And so my sort of theme is that this is what we should think of as the intersection number. The intersection number itself, like we saw in the example, is not homotopy invariant because we can lose things at the end, but it's swapped for this. So I have a sum of two non-negative things here. Neither's homotopy invariant, but their sum is. And so I get out of this that this thing is a a topological upper bound on the number of intersections. And in particular, if it's equal to 0, we know that no intersections can ever appear between these things, even when u has an n going to the puncture. So I will stop there.